sorry about that technical difficulty. So continue where I left off. So now we have that definite interval to calculate an area with a right function and a left function. And so here's an example to use that with to get the answer. Okay, so example, find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Okay? Okay, good. Okay, so let's do this example. Solution. Okay, so first let's draw a picture of what's happening here. So we have the x-axis and we have the y-axis. And so y equals x minus 1, looks like that. And then y squared equals 2x plus 6, looks like that. Okay, so this is y squared equals 2x plus 6. And so on your graphing calculator, you could just graph these two functions, okay? So you can just go y equals, and you plug in two separate lines, y equals this, and well, no, okay, so you would have to solve in terms of x, and so you would have x, for this one, on your calculator, you would need to do x equals y plus 1. And for this one, you would do x equals y squared minus 6 over 2. And so just solve both of them for x. Okay? And so when you graph those two in that way, you graph those curves, and then now the area between them, enclosed by the line and the parabola, is, we want to find the area of that shade region there. Okay? So now you can ask the question, where did the two graphs intersect? You could also graph this probably using pre-calculus. Okay, so let's find the intersection points of those two graphs. So first we set x1 equal to x2, where this is x1 and that's x2. Then that means y plus 1 is equal to y squared minus 6 over 2. And then we solve for the y that satisfies this equation. Okay, and that's the y value that these two functions have in common. Okay, this y value and this y value. Okay, so then you solve for y, and so I'm going to move everything here on the right side. So you get, actually I'm going to multiply both sides by 2. You get 2y plus 2 is equal to y squared minus 6. Move everything to the right side, you get 0 equals y squared minus 2y minus 8. And so 0 is equal to y minus 4 times y plus 2. And so then you get minus 4y plus 2y is minus 2y, minus 4 times minus 2 times positive 2 is minus 8. And so you get, okay? And then y minus 4 times y plus 2 equals 0 means either y equals 4 or y equals negative 2. Okay? So those are the two y values, where x1 equals x2. So if y equals 4, then we could say x equals 5. So you have 5 comma 4 here. Now if y equals negative 2, then that would be negative 1. So you get negative 1 comma negative 2. Okay? And so those would be two intersection points. And so with this work, you find those two intersection points. Okay, good. All right, so now we found those two intersection points. And next, let's find the area of that shaded region. Okay, good. Okay, so capital A is equal to the area of that shaded region, and it's equal to the definite interval from this y value, negative 2, to this y value, 4, of the right function, which is x minus 1 minus, oh sorry, this is with respect to y. So the right function is y plus 1 minus the left function, which is y squared minus 6 over 2 dy. Okay? And so this is from our previous equation, integral from a to b, c to d of f of y minus g of y. That's the f of y, the right function, minus g of y, the left function. Okay, so let's find the value of the step integral. So first I'm going to simplify the integrand function. You get y plus 1 minus y squared over 2 minus negative 6 over 2 is plus 3. That's dy. That's equal to the definite integral from negative 2 to 4 of negative y squared over 2 plus y plus 4 dy. And so then that's equal to an antiderivative of that function, which is negative y cubed over 6 plus y squared over 2 plus 4y, evaluated from negative 2 to 4. And so then that's equal to, you plug in 4, you get negative 4 cubed over 6 plus 4 squared over 2 plus 4 times 4 minus, plugging in negative 2, you get negative 2 cubed over 6 plus negative 2 squared over 2 plus 4 times negative 2. Okay, and so you calculate this and you get negative 64 over 6 plus 8 plus 16. So that's 24 minus 10 and 2/3. So 24 minus 10 and 2/3 is 13 and 1/3 minus this. And so this is 4 over 2, which is 2. 2 minus 8 is negative 6. This is negative 8 over 6. The negative of negative 8 over 6, which is positive 8 over 6, which is 4/3. So again, this is 2/3. This is 2 minus 8, which is minus 6, plus 4/3, which is negative 4 and 2/3. Yeah, so you're just doing calculations here. It's 13 and 1/3 minus negative 4 and 2/3. That's plus. So two negatives become plus. So it's 13 1/3 plus 1 2/3. 13 plus 4 is 17. 1/3 plus 2/3 is 1. 17 plus 1 is 18. So the sum of those two mixed fractions is 18. And so the final answer is that the area of that shaded region is 18. And you could use your calculator for this. You could write it out. You get 18. Okay. And so that is the answer to that problem using the formula at the end of the last video. Right, that formula was the integral from c to d of f of y minus g of y dy. That's the area. Okay, so we use that one right here in this problem. It's the f of y minus g of y integral from c to d dy. So this is c and this is d. Okay. And so when you're done with that example. So let's take that next thing. Okay, so just as a note as to why we solved that problem the way we did. If we look at the same functions again, y equals x minus 1, and the parabola y squared equals 2x plus 6, right? Now, if instead of integrating with respect to y, we chose the original method, integrating with respect to x for the top and bottom function, we have to look at this point here. And so let's look at this vertical line here. To the right of that vertical line, the top function is this parabola, and the bottom function is this line. And you could integrate with respect to x from here to here, and you could get the area of that region. But now if you look at this region, the top function is the same, but now the bottom function is no longer the line, it's now the bottom part of the same parabola. And so to integrate with respect to this part, to integrate this part, you'd have to integrate from this x value to this one, and you'd have to say that the top part was y equals the positive square root of that, and the bottom part was y equals the negative square root of that. So anyway, the top and bottom function changes to the left of this line. And so to find the total area of the shade region, you would have to separate it into two subregions and find the areas A1 and A2 of them respectively, and then add the two areas to get the total shaded area. Okay, so to integrate with respect to x in this problem, it would take a lot more work because you'd have to find the areas of two regions and then add them. Okay, while the original method, we just found the area of the whole thing with one definite integral. This would require two separate definite integrals and then having to add them. It would take more work, and calculating A1 would be more difficult because the function you'd be dealing with, the functions you would be dealing with, but the top and bottom function would be more difficult to handle. And so this other way would be a lot more work. And so the way we did it on the last board is the better way to solve this problem. Okay, so that's just a side note to that problem. Okay, and so that is the end of 7.1. Yeah, let's keep going. Okay, so 7.2 is on volumes. Okay, so 7.2 is on volumes. Okay, so okay, so we have a good idea what area is, right? And so here we're going to explain what volume is. So so we're going to start with something called a cylinder. Okay, and so let's say we have one base called B1. Let's say we have a congruent base B2 in a parallel plane. So like this. Congruent, meaning it's the same thing, just moved. And so let's say we take the same B1 and we move it up and we call it B2. A cylinder would be the amount of, so a cylinder would be that shape, where we kind of just took this region and it kind of stretched it out from B1 to B2. That shape is called a cylinder. Okay? So the cylinder consists, so a cylinder consists of all points on line segments that are perpendicular to the base and connect B1 to B2. Okay, so for instance, this would be a point on B1. This would be a line perpendicular to the base B1, and then it would, it would touch the second plane B2. And so the line segment going from this point to that point now has a bunch of points on it. All those points are on the cylinder, and the cylinder consists of all points on such line segments. So if I took another line segment, let's say from this point to this point, then all the points in that line segment are points in the cylinder. And so if you kind of added up all the line segments from point here, perpendicular to the base and going to B2, then that would consist of the entire inside of this cylinder. And so you get the entire thing. And so what I'm shading is not the surface, I'm shading the entire inside and surface, everything about that three-dimensional shape called a cylinder. Okay? And so that defines what a cylinder consists of, all the points on such line segments. Okay? So if the area of the base is capital A, and the height of the cylinder is little h, meaning the height from B1 to B2 is h. The volume of that cylinder is equal to A times h. So the volume of the cylinder is equal to the area of the base times its height. meaning the length of some line segment that starts at B1, goes perpendicular in the perpendicular direction to B2 and stops at a point in B2. The length of such a line segment, H, is the height. So V equals A times H. Okay, so one example of a cylinder is if the base is a circle with a radius little r. Okay? Then the cylinder will have some height h, and so then the cylinder would look like this, right? And now the area, the volume, would be A times h, and so the area is pi r squared of the base times h, the height. So the volume of a cylinder with the base of the circle, as a circle, is pi r squared h. Okay? If you had the base was a rectangle, right, then you'd have another rectangle for the other top part, and then you'd have the height, which is h. Then the area of the rectangle would be length times width, and so the volume would be the capital A, the area of the base, times the height, and that would be L, length times width times height. So the volume of a box like that would be the area of the base, which is a rectangle, which is length times width times the height. So length times width times height is the area of that. Pi r squared h is the area of that. Those are two types of cylinders. This is also called a cylinder. This box is also considered a cylinder because it's defined in such a way, like this. You can make it like that. Okay. And so looking at a little bit weirder of a shape, not that weird. If you have a base that looks like this, then you have another congruent one that's parallel to it. Then you have the height, which is h. Okay. Okay, the height is h. Then the area of that is, the volume of that is equal to A, which is the area of the base, times h. Okay, this is B1, that's B2. Okay, so we have V equals pi r squared h for this guy, and we have V equals A times h for that guy. Okay, so these are three examples of cylinders. Okay, and so the cylinders are going to be like the building blocks of the three-dimensional objects that we're going to find the volume of, okay? So what we're going to do is we're going to take a three-dimensional object and we're going to find its exact volume by cutting it up into cylinders and approximating the volume by adding the volumes of approximating cylinders. Okay, so for area we add the areas of approximating rectangles. For volumes we add the areas of approximating cylinders. Okay, so let's go to the next word. Okay, so to make this a little bit simpler, let me go to the definition. Let capital S be a solid that lies between x equals A and x equals B. If the cross-sectional area of S in the plane P sub x through P sub x through x and perpendicular to the x-axis is A of x, where capital A is an integral, where capital A is an integrable function, then the volume of S is capital V, which is equal to the limit as the max delta x of I approaches 0 of the sum from I equals 1 n of A of x of I star delta x of I equals the definition from A to B of A of x dx. Okay. Okay, so this definition, let capital S be a solid that lies between x equals A and x equals B. If the cross-sectional area of S in the plane p sub x through x and perpendicular to the x-axis is A of x, where A is an integral function, then the volume of S is capital V, which equals the limit as max delta x of I approaches 0 of the sum from I equals 1 to n of A of x of I star delta x of I, which equals the definition from A to B of A of x dx. So let me illustrate this with a picture. Okay, let's go with the x-axis and the y-axis. Okay, so we're start by drawing the y-axis. So let's draw a three-dimensional region on the board. Okay, so that's one part. That's the left side of the three-dimensional region. Now let's draw the right one. Okay, we had some perspective maybe. Not really an art major here. Okay, so that's our three-dimensional region. This is the front, this is the back. So let's look at a point X on the x-axis, okay? Now let's look at a plane through the x-axis that cuts into the three-dimensional object. So if you think of an apple, and if you had a knife and you took the apple and you just cut it and you sliced it vertically, right, perpendicular to, let's say, the table, then that would be like this cross section, what we're doing here. If you take this X, right, and let's say this object was like the apple. Now let's say you had a knife and let's say you cut through the object in a perpendicular direction. So it went through this point X on the x-axis. But just because of perspective, I'm going to say that this axis is kind of going out at an angle. So when we cut perpendicularly, I'm going to make it on an angle, but I'm still kind of cutting it perpendicularly. So let's say the cut is through this plane here. Okay, so see where the dotted line is? That dotted rectangle is inside of a plane, and that's the plane upon which I've cut through that three-dimensional object. And then let's look at the parts of the object that got cut from when I cut into it. Okay? So this is the region, this thing here is the part of the three-dimensional object which was cut when I cut through that plane and through the point X on the x-axis. And A of x is the area of that two-dimensional surface that was on the side, on the part of that cut. Okay? And P sub x is the plane upon which the kind of the knife goes through. So if the apple is on the table and I cut it, the plane through which the knife goes through three-dimensional space, through that plane, that's the plane P sub x. And the point upon which the knife hits the x-axis, that's the point x, okay? And so if I always make this cut in this particular direction, right, for each x on the x-axis would have its own P sub x, its own plane through which I make the cut, right? So if I cut the apple directly through the middle of the apple, right, the point upon which on the x-axis that cut goes to the x-axis would be the x. Now if I move the cut a little bit to the side, it's kind of like in parallel with the last cut, but there'd be a different x and there'd be a different plane, right? So on each x, value of x on the real line, it has its corresponding P sub x, the plane through which the cut is made, okay? And the plane through which the cut is made intersects a different part of the object, right? So as I cut to the right or to the left, there's going to be a different piece of the object through which the cut touches the three-dimensional object. And so A of x would be the area of the two-dimensional surface upon which the cut intersects that object, depending on where in x your cut is going through, okay? And so that's what's happening here in this definition. The A of x, right? The A of x here is the cross-sectional area of S in the plane piece of x through x, and perpendicular to the x-axis. This is perpendicular to the x-axis. Okay, so we got up to this point where capital A is an integrable function. So here, this capital A, you can find this capital A by, so you can integrate that function, is what that means. Then the volume of S is capital V, which is equal to this definite integral. And so I will not expect you to understand what that means. And so you can just say that the volume is equal to definite integral from A to B of A of x dx, where A is the leftmost point upon which you'd make a cut, and x equals B is the rightmost x value upon which you'd make the cut, right? So if you're thinking of the three-dimensional object from this x value to this x value, right? You're going from here to here, then you're integrating from A to B of A of x dx. Okay, it's kind of like this cross-sectional area is sweeping from x equals A to x equals B, and as you sweep that region with area A of x from x equals A to x equals B, you're kind of covering the entire three-dimensional object. Okay? Okay, so basically we sum up this page by saying capital V is equal to that definite integral. Okay, and so let's talk a little bit more about this on the next board. So notes. Okay, so notes. Using capital V is equal to the definite integral from A to B of A of x dx. Remember, this is what I was saying. Remember, A of x is the area of a moving cross section obtained by slicing through x perpendicular to the x-axis. Okay, perp is short for perpendicular to the x-axis. Okay, a note. For a cylinder, if the cross-sectional area is constant, then capital A of x is equal to capital A for all x. So the volume of capital V is equal to the definite integral from A to B of A of x dx. And so that's equal to capital A times B minus A. And that's equal to capital A times H, where H is B minus A. Okay? So, for instance, let's say you had a circle here, and so let's say, and then you kind of just, the cylinder is one where you have this as pi times, let's say the radius is 1, so pi times 1 squared, which is pi, right? That's the area of the base, right? And so then let's say this is the x-axis and that's the y-axis. And so then let's say this is x equals 0 and let's say this is x equals 5. Then the volume of that cylinder, well, it would be the integral from 0 to 5 of a of x dx, but the area is constant. It's just the same. The cross-sectional area is just the same, the area of the same circle, because you're just sweeping it. It's always staying the same. The area is always pi. And so this is the differential from 0 to 5 of pi dx. And what that equals to is pi times 5 minus 0. That's pi times 5. Right? 5 is the height. Even though it's horizontal, even though we're going in this direction, it's the height. The height is 5. And so you're taking the area of the base, in this example, which is pi, and multiplying it by the height 5. And so that's an example of how you can take the volume. If the cross-sectional area is constant, the volume is that cross-sectional area A times h. Okay? So that's a second note about calculating volumes. Okay, and so let's do an example. Calculating the volume using this formula. So an example, show the volume of a sphere is of radius r is capital V equals 4/3 pi r cubed. Okay, so show the volume of a sphere of radius r is V, capital V equals 4/3 pi r cubed. Okay, so volume of a sphere of radius capital R. So let's draw a picture of the sphere. Okay, so let's find the volume of the sphere. So to find the volume of the sphere, let's note that if you were to take a cross-sectional area, let's say this was an X, and you were to take a cut through here, right? Then what you would get is, right, a circle. And so you want to find what is the area of that circle, right? The area of that circle would be A of X. The area of that shaded region, or that cross-sectional area, would be A of X. So, and so here, A of X, which is that cross-sectional area, is equal to pi times r squared. I mean, not pi times r, little r is the radius of the entire thing. So little r would technically be the length of that, right? So what we want is the radius of this circle. And so what we have is a right triangle see this triangle here, we have a triangle here, where this is the radius of the circle. This is the x coordinate of your point. And this is actually the radius of the sphere. And so this is a right triangle. So that means that this height is the square root of r squared minus x squared. Because then by the Pythagorean theorem, that works out. Okay, so this is the radius of this cross-sectional circle. So the area of the cross-sectional circle is pi times this radius squared. So it's pi times the square root of r squared minus x squared, which is pi times r squared minus x squared. So that's A of x. So the A of x, the cross-sectional area, the area of that thing, is pi times little r squared minus little r squared. And so capital V, which is the volume of the sphere, is a definite integral from the smallest x value, which is negative r, to the largest x value, which is r. A of x dx is equal to a definite integral from negative r to r pi times r squared minus x squared dx. Okay, good. Okay, so now, let's say this is the pi r squared, differential from negative r to r of 1 dx minus pi times differential from negative r to r of x squared dx. So just to calculate this differential. And so this is equal to 2r. So this is pi r squared times 2r. Where you get x evaluated from negative r to r. So it's just r minus negative r, it's 2r. And this is minus pi times x cubed over 3 evaluated from negative r to r. So it's equal to 2 pi r cubed. 2 pi r cubed minus, this is pi times r cubed over 3 minus negative r cubed over 3. Okay, so then this is equal to 2 pi r cubed minus, and so negative r cubed is negative of r cubed, and so r cubed over 3 minus negative r cubed over 3 is r cubed plus r cubed over 3 plus r cubed over 3, which is 2. This is 2r cubed over 3. And so with some algebra, you just get 2 pi r cubed minus 2/3 pi r cubed, and so that is 6. That's 6/3 pi r cubed minus 2/3 pi r cubed. That's equal to 4/3 pi r cubed. That's the answer we wanted. So we got the volume of the sphere is equal to 4/3 pi r cubed. Okay? And that finishes that example. So we showed that the volume of a sphere of radius r, the volume of a sphere of radius r is 4/3 pi r cubed. We're done with the example. Okay? So we'll stop here, and next time we'll continue this section.